The question was asked, can we mock this up in our own, in some kind of scale model? Yes, we absolutely can, and maybe that's the best thing to do. So here I'm going to do it. I've given Crash Bandicoot a flashlight here. He's shining the flashlight down onto the ground. And I've set up two little Lego chess pieces on the ground where we see that they're casting a shadow. I'm going to use this technique to triangulate back from those shadows back to the location of the light source. And then we'll measure everything and see how well I did. It occurs to me that it may not be as obvious to everyone as I think it is about the shadow thing. So let me illustrate here with a piece of yarn. I have connected one piece of the yarn to the light source, the flashlight, and I'm holding, you see I'm holding the other end against the very end of the shadow. And I think you'll see the yarn goes right across the top of the Lego, showing that straight line connection. If that piece of yarn is a beam of light coming from the flashlight, that beam of light goes straight, and wherever it is blocked by the Lego, that is where the shadow is cast, right? And so if I use the yarn to visualize a perfectly straight beam, we should be able to show where that beam crosses right over the top of the Lego and hits just past the end of the shadow. What we're mocking up here is being in two different locations. So if one person in this is in one city, here represented by the white object, and measures a shadow there, then another person will be in a different city and measuring their shadow. And that's what we're mocking up here. The last piece of data we're going to need to do this triangulation is the distance between those two cities, or the distance between the two Lego chess pieces. So here I'm measuring along, and we should be able to take a look there and get the actual distance between those. I'd like to point out that doing all of this in 3D is absolutely possible, but it makes it more complicated. I have deliberately arranged things in a straight line here so that I can do all of this in a two-dimensional diagram, and that'll make this much easier to do. I've used my measuring tape to create a straight line away from the light source and placed my two shadow objects along that line. This is exactly how we've set things up by having everyone do their shadow measurements at local noon. That means that in that scenario, the sun will always be directly south of you if you're up north like me, or at least in a direct north-south line, no matter where you are. And that creates this two-dimensional scenario that is so easy to do in a simple diagram. So there was some question about how does all this work. So let me try to go through this again. And forgive me if this is too basic. Just skip ahead if you know this stuff. But just in case you don't, let's start with what is a shadow, because we are using this shadow to try to get the angle to the sun. So how am I able to do that? Why does the shadow do that for me? So here in my diagram, this is the sun, it's the light source. In the scaled mock-up, that would be the flashlight. And here we have some object. This is our stick. In the scaled mock-up, that was my little Lego chess pieces. Now, the light from the light source radiates outward in all directions. And let's just draw a few beams of light coming from the sun. Got some different beams, and this is where they go. Like in my flashlight, it doesn't go in all directions. It only goes, sort of in this sort of direction. The sun would go everywhere. I didn't draw the beams over here, but there's beams over here too. We don't need those. What I'm showing is that some of the beams make it all the way to the floor, but some of the beams are interrupted by the stick, right? Where they are interrupted, they cannot make it down to the floor. So this beam makes it all the way down to the floor, and this beam makes it all the way down to the floor. But this one is blocked by the stick. So over here, we have sunlight hitting the floor. And here we have sunlight hitting the floor. But right here, in this region, the sunlight is being blocked by the stick, and that creates the shadow. The shadow is whatever is blocking the light, creates that pool that the light cannot get to, and that's the shadow. Okay, so this line right here, notice that it is in fact a line that goes from the tip of the shadow, crosses right over the tip of the object, and then continues on to the sun there. The angle of that line is the angle of the direct line from the tip of the object, tip of your stick, up to the sun. So that is the angle that we are trying to use here for our purposes. All right, so that is why the shadow's length can be used to get that angle of where the sun is. And now let me show once again how we're going to use just measurements of the shadows to get the angle without doing any math, no trigonometry. We're just going to use a protractor. Okay, so here's how we do it. We have our stick and we have our shadow. And what we'll do is just draw, as I've done here, a scaled diagram of these. We have a known height for the stick. We measure the stick, and then in our diagram, we'll scale that to some known scale. And we'll do the same thing for the shadow. We measure the length of the shadow, and we will use the exact same scale to draw a scaled representation of the length of the shadow. All we do now is connect the dots with a straight line, and that is, this line here represents the line that I said was going to point back straight up towards the light source, off in that direction. The angle of this line is the exact same angle as the light was coming in from the light source. So to measure that angle, we will just drop a protractor, and in this example, it looks like I got about 39 degrees. Okay, but this is just a made-up example. Now, when we do this, what we've done is measured the angle that the light is coming in towards our object. Okay, that is the angle from the light source to the object. How are we going to use this to calculate the height of the light source? We can't use just this. We're going to need a little bit more. We have to do what's called triangulation. So how does triangulation work? The idea is we have two different locations that are a known distance apart. And at each location, we have a known angle. So at this location, we have one angle, and we will just draw a line at that angle. And at the other location, we have a different angle, so we'll move on over there, and we'll draw that other location's angle, and there you go. So this is, we took two different observations. There was a shadow cast over here, and we measured that, and we used our protractor to get the angle of the shadow at this location. And we also had a shadow cast at this spot, and once again, we measured the length of the shadow, used the protractor to find the angle. The only other piece of information we need is the distance between these two. That will set the scale for this whole diagram. And then wherever these two lines cross, that is where the light source actually was. So we now have a scaled diagram of exactly where the light source is, and we can use that to find the height above the ground of that light source. What I've been talking about, we can measure the height of it above the ground. So we've got 6.1 centimeters up above the ground. We will just use the known distance here to set the scale of that measurement, and then we will have the actual height of the light source. Okay, so let me take you through a bit of an example here. This is the example that I showed me setting up in my office with the Legos. I had two Lego pieces. The Lego pieces are The white one and the black one, they are 7 centimeters tall. The easiest way to set this up, what anyone can do, is just get a piece of paper and a ruler and work out a scale so that you can draw a scaled down diagram of exactly what you measured. I'm using PowerPoint here. You can use whatever you want. I just wanted a way to show this easy. So what do? I have 7 centimeters for my white bishop's height, and I will draw a line at the scale that I have chosen. I have chosen a scale where 1 inch equals 2 centimeters. That's my scale that I'm using for my diagram. And so my 7 centimeters then is 3.5 inches equals 7 centimeters. Okay, that's the scale that I chose. So I drew a line 3.5 inches tall. Now, the shadow I measured the shadow at 12 centimeters long, and I'm going to use that same scale. So using that same scale, 12 centimeters, how many inches is that going to be? Using this scale, that's 6 inches long. And so I created my, my shadow line, the horizontal line is 6 inches. All I've got to do now is connect those, and that line is the angle back up towards the flashlight. I will bring in my protractor to measure the angle, and I am literally just using a picture of a protractor. If you don't mind a little trigonometry, you can easily do this with a calculator and get a more accurate result, but that's okay. This is going to be just fine. So here we go. I'm going to call that about 30 degrees. Okay, so that's 30 degrees. The white bishop, therefore, the white bishop has a 30-degree angle up to the light source. Doing the same thing for the black bishop. Again, 7 centimeters tall, and its shadow I measured at 8.4 centimeters long. You don't have to get all that precise with it. That should be good enough. And so using that same scale, 8.4 centimeters on my scale, which was, again, divide by 2, right? So 4.2 inches. And so I've created a line 4.2 inches long right here for the shadow. Now I just need to connect those and measure my angle again. Bringing in my protractor, and this time I'm calling that 40 degrees. So the black bishop, I have measured now that the angle to the light source was 40 degrees. Okay, now that we've got those two angles, we bring it into the triangulation phase. So here we go, we're going to triangulate. I have measured the distance between those two Legos on the floor at approximately 66 centimeters. So 66 centimeters separates them. That is going to scale my little diagram here. Now, I can't use that 2 inches or that 2 centimeters for 1 inch scale on this diagram. It's not going to fit, right? This is a much larger diagram. So I need a different scale. I chose a scale of 30 centimeters to an inch. So I have made these marks. They're 66, right? They're 66 centimeters apart. And so I divide by 30, and that's going to give me, for my scale, that's going to make me at 2.2 inches apart. So this line down here, these two lines are 2.2 inches apart. And I put them over on the side of the diagram to give myself plenty of space for where the light source is going to be over here somewhere. Now at the white bishop, we said we had an angle of 30 degrees. So here's my protractor. Let's shoot a line at 30 degrees. And over at the black bishop, we measured 40 degrees. So there you go. There's our 40-degree line. Now, Where those two lines intersect, that is the location of the flashlight. And I have now reconstructed my diagram. This is a scaled diagram of exactly what the scenario was like in my office when I did this. So let's keep going. We are now trying to assess what is the height above the floor, and I will now just measure that. I have measured this line at 4.2 inches scaled, right? This is in my scaled diagram. I have 4.2 inches scaled. Let's convert that back to our real world centimeters and see what we get. I had used a 30:1 scale here, so this distance was 2.2 inches, and I'm just showing here 66 centimeters equals 2.2 inches. Therefore, my scale is 30. 30 centimeters is 1 inch. So how do I convert this? I just take my 4.2 inches times my scale, and I come up with 126 real world centimeters. So according to my triangulation technique with the protractors in PowerPoint here, my result was 126 centimeters. So how did I do? That's the big question. I measured the height to the flashlight using a tape measure, that same tape measure, and I measured it at 123 centimeters. So it was not perfect. Some of my guesstimations were not dead on here. But how bad was it? The error can be expressed as a ratio or as a percent, like so. The measured amount I got here, or the calculated amount, if you want to call it that, I got was 126 centimeters. The actual was 123. As an error amount, that is this, or in percent, 2.4%. So I was off by 3 centimeters, and that might sound like a lot, but recognize that's within 2.4%, and that's not too shabby. That's definitely pretty good. Anything within 10%, is going to be decent, I think. So there you go. That's how you do it. That's how you do a scaled down version of it. And what we're going to do is do the same thing with the sun as our source of light, and much larger distances between different cities is the goal. We will take these measurements in different cities, and then we'll use those to triangulate the location of the sun and calculate the height of the sun above the flat Earth, and hopefully we'll get close enough. We'll get something like this level of precision. We should be really happy with that, right? If it's 3,000 miles up there and we're off by a couple hundred miles, whatever, right? That's good. We'll know like what the ballpark is for it, at least. Okay. All right. Hopefully that helps. Let me know if you want to see more. I can do this again with math. If I find some time, maybe tomorrow, I will try to redo this again using the actual trigonometry method instead of just the protractors method, and see if we get how different that really is. That could be interesting. And also, there was a request maybe to explain how the ball method works, where we get the radius of the globe by doing this. Because frankly, in my previous video, I did not explain that at all. I just sort of took it for granted that the globers kind of already know how that works. But yeah, maybe we don't all know. Maybe that's something we should illustrate. So if you want to hear that, let me know down in the comments and I'll cover it.